The GAMMALN.PRECISE function within Excel allows us to take the natural logarithm of the gamma function. The function is quite simple as it only takes in one argument, being the x value of our gamma function. So we write GAMMALN.PRECISE and we give it one argument, the x value. So let's take -3 as the x value here and pull this down. Now, as you can see, we are only getting results for absolutely positive numbers as the x value. Now, you might be wondering, what is the difference between this GAMMALN.PRECISE function and the regular GAMMALN function? So let's test that out. So we take the GAMMALN of this x value and we pull this through as well. At first glance, there doesn't seem to be any difference. Let's select these values and increase the number of decimals we are seeing. Now, as you can see, even when we increase the decimals, the number of significant characters remains exactly the same. I think in earlier editions of Excel, there actually was a difference where the GAMMALN.PRECISE function would return a more precise result, meaning it gave like 14 digits of precision, whereas the GAMMALN function gave 16 digits of precision. But as far as I have been able to experiment with these functions, the results always turn up exactly the same. So as far as I can see, they are exactly the same. So feel free to use the GAMMALN and the GAMMALN.PRECISE function interchangeably. Arguably, you might want to use the precise function as that was the one that was latest introduced. Okay, so here we have GAMMALN.PRECISE and here we have GAMMALN as a function. Now, where do these results come from? What does it mean to take the natural logarithm of a gamma function? Well, the gamma function finds its origin in the factorial function. And so the factorial function is written with the exclamation mark. And it means we input an integer in the factorial function and out comes a result. And the result is that integer multiplied by each integer minus 1 that came before it. So we can use the fact function to take a factorial of a certain number. So let's take it of -3 and pull this down. Now, as you can see, we do not get any results for negative numbers, but for positive numbers, including 0, we are actually getting results. Now, how are these results calculated? Well, like I mentioned, we take the current integer, in this case 3, and then we multiply this times 2 times 1. So each time subtracting 1 from the integer, and that's how we end up with the 6. So 3 factorial equals 6 because 3 times 2 times 1 equals 6. Now the factorial of 4, let's calculate that one as well, is 24. So one thing you might notice is that each factorial is equal to the current digit multiplied by the factorial of the digit that came before it. So in this case, 24 could also be calculated by multiplying 4 times the factorial of x minus 1 being 3. However, something that is not possible to do is taking a factorial of a decimal number or of a negative number. Now, Excel is still returning results here for a factorial of 2.5 and 1.5 and 0.5, but those are not mathematically sound, as what is really going on is Excel is taking the lower bounds of this 2.5, so it's reducing it to 2 using a round down, and then taking the factorial of 2. That's really what's going on behind the scenes. So these results are not actually correct. The factorial of 2.5 is not 2. So mathematicians were looking to solve this. They wanted to get an accurate number for the values that came in between two integers, such as 1.2, 1.5, 3.6. And they were also looking to solve the factorial for negative numbers, so minus 1.5, etc. So they came up with the gamma function. Now, in essence, the gamma function is really x minus 1 factorial. So let's calculate this one. So we take the factorial function of x minus 1 and we close the parentheses. We pull this through, we get some results. Now let's do the same thing for the gamma function. So there is a built-in functionality in Excel to calculate the gamma function that is equal sign gamma. We provide the value, in this case -3, and we pull this down. One thing you might be able to notice is that it does indeed match up for those integers that are whole, right? So each time these match, but they don't match for those decimal values, just like 1.5 and 2.5. But remember earlier I told you Excel was cheating a bit, and so the results it was returning were incorrect. So the factorial of 2.5 is not 2, but actually the gamma of 3.5. So that would be 3.323, etc. Right? Because remember, the gamma function takes 1 from x, right? So when we want to take the factorial of 2.5, we need to take the gamma function of one that's one bigger, right? So 1.329 is the factorial of 1.5. Now what we're doing is we're taking the natural logarithm of the gamma function. So that's the ln. And so for this, we take the ln function and we input whatever was returned by the gamma function and pull this through. Now, one thing you can notice is that you cannot take a logarithm of a negative number. So for those results, we get an error here. But we can actually take a logarithm of these positive values. So where the gamma function turns a positive value, such as with minus 1.5, we can actually take the natural logarithm for that. And notice that both the GAMMALN.PRECISE and GAMMALN function do not return any results. So in this case, Excel is actually incorrect. It should actually calculate values here, but that's not happening because the GAMMALN.PRECISE and GAMMALN function only return results for strictly positive numbers. So that's something you want to take into consideration whenever working with the GAMMALN.PRECISE function. If you found this helpful, consider subscribing to the channel for more videos like these. You can also leave a tip using the PayPal link in the description. Thanks for stopping by. Feel free to watch this recommended video.